First question is, we've got the project proposals due tonight. Any questions about the project proposals? Anything that needs to be clarified or anything like that? You've got 3 pages plus references. I do not want to see 4 pages. Okay. Again, you want to convince us that you know what you're doing. You know that means some kind of you have some kind of a clear plan of what you're going to do from now till the completing. A clear plan does not mean every day what you're going to be doing, okay, or even every week what you're going to be doing. But clearly that you've got a next direction that's going to take you a chunk of time, and that maybe you've got a vision that if this doesn't work, I'm going to try that. That's the level of plan that I'd like to come away knowing that you know what to do with. And ideally I'd like to see evidence of work you've done on the project so far. If you've got some partial results, some graphs, something or other, this is a good thing to put in there. Okay? If you've done some background reading, it's good to show evidence of that. And do what you can do in 3 pages. So the 3 pages of most interesting stuff that you have is what we'd like. Any questions about the proposal? Yes?
So I wanted to ask about the fact that a few ideas we were exploring, it was difficult to gauge the feasibility of it, or if going down the line would it actually be possible. So do we mention that in the proposal, or do we keep it?
So something to the effect of, we've got 10 ideas and we'll see what we do is not as good as saying, this is what I'm really interested in, but this is what these are what the roadblocks might be. I don't know if we're going to be able to overcome it. If we're going to can't overcome it, we're going to do this. That says something, okay? But a laundry list of what other things you can do is probably not good, okay? And, again, if you have evidence that you've explored some of these things for why you think you're going to be able to do it, you've done some preliminary experiments, some preliminary results, okay, that would be good. Okay, any questions? Okay, today I'm going to have to, after class, run to my office because there's a call that I have to be on at 11. If you want to discuss your project with me afterwards, run with me, or and if necessary, wait until the call is over. Okay? Any questions about that? Okay? Fair enough. If not, what I'd like to talk about today for real is problems on classification, particularly logistic regression. Last class we talked about linear regression. We talked about how we could solve it using fancy linear algebra or pretty straightforward gradient descent search, and something about how we would formulate linear regression problems, how you have to massage the data to help make it better. Today we're going to talk about using these kind of linear models for classification problems. Classification problems are ones where you're given examples and you want to try to identify, what class it's in. Some of them are binary problems, things like, looking at something, is it male or female? Is a voter going to vote Democrat or Republican? Okay, is a biopsy sample cancer or benign? Those are binary classification problems. I guess in your last homework, you were dealing with classification problems that were multi-class things. So given an image, was it a cat? Was it a car? Was it an airplane? Okay? Or given a text, was it a news article or a sports article or something like that? So those are classification problems. The input is a record and the output is assigning a label to it. Okay, and this is kind of a bread and butter data science task. Let me start by showing you a way you might have used linear regression for classification. And let's see whether it's a good or a bad idea. It could be, remember, linear regression was supposed to take a record and predict the target value. What if your target variable was a binary value between 0, where maybe the positive class got 0 and the negative class got 1? Okay? You could imagine then training a linear regression model where the x values were all the features of the items, and the y thing you're trying to predict was the target variable. Okay? Now again, this works for binary classifiers, okay, where you've got two classes, positive and negative. For three classes, or multiple classes, this might be a less good formulation. But any questions about how you could use linear regression for this? Okay? Now what would happen? Okay, again, you'd have a world where, let's say there was some x value, okay? You had, in this case, it was only a one-dimensional data set, okay? And you had positive examples and negative examples, okay? And you found the best fitting line on it. Let's say we're trying to tell the difference between women and men, okay? The women are on the left, the men are on the right, okay? Is this linear regression line make for a good classifier? How would we use it as a classifier, and what's good or bad about it? If anybody has any, I think. How would you use it as a classifier to decide whether something's male or female? Yeah?
Depending on the x value, you could check the corresponding y.
For the x value, I predict the value y, and I guess what you'd say is if it was above 1/2, it was male, and if it was below 1/2, it would be female, right? Okay, so this feels to me like it could work. What's wrong with this, or what's disadvantageous about this formulation? Anyone with a hand? Okay. There are a couple things that are kind of weird about it. What happens if we add Superman to the training set? What is you guys are familiar with the Superman? Okay. Superman is such a man that he would be out where? His maleness is presumably out here or someplace, something like that, right? What is going to happen to the regression line when we add Superman to the training set? Okay, yeah? It'll skew more towards that to try to capture this outlier, okay? And is that what we want? No, okay? Adding Superman to the training set would make it worse for us, right? Okay, we're not trying to, what is the other observation? This regression line is trying to predict the femaleness, maleness of the item, where with a classifier, what you really want is a separating line, okay? A line that kind of cuts, but tells you where the boundary is between one and the other. There is kind of a boundary implicit in the regression line, but it's not kind of the thing that you're optimizing for, okay? Any questions about that? So this way of doing classification wouldn't work very well. Wouldn't work as well as we would like, okay? Any questions about that? So again, when you're building a classifier, what you really want to learn is not a line that fits the data, but a line that kind of partitions the data. Okay, you want to try to identify a boundary line, a decision boundary, separating the positive class from the negative class. And logistic regression is the kind of a linear, regression-like method that will try to find the best separating line. Okay? Any questions? Now, just like with linear regression does not necessarily mean that you're producing a line that's actually straight. You're producing a linear function of the input variables. And if you have nonlinear variables, nonlinear functions of your input variables, you can get nonlinear boundaries. So in this classification, okay, we have the positive examples are all near the origin. Okay, the negative examples are further away. The right decision boundary is going to be, if you lie within this circle, you would be positive, and if you lie outside the circle, you're negative. If your variables contain, x squared and y squared, okay, the real question for the circle is defined by x squared plus y squared equals the radius, okay? If x squared and if x1 squared and x2 squared were, added to your input set, which are clearly functions you could define on the initial variables, you could construct these kind of decision boundaries if you want. Okay? Any questions? But how do we get a, linear regression to try to think in terms of decision boundaries? And it's based, logistic regression is based on the logit function, which I know we talked about before. But it's a way of converting any real variable to a probability. Okay? So, the logit function is 1 plus e to the minus perhaps a constant times x or perhaps x. Okay? What does this logit function do? If x was equal to 0, what do we get? E to the minus 0 is e to the 0, which is 1. 1 over 1 plus 1 is a half. So that would say that if we have a decision variable, if the value of this was 0, we're going to get 1/2. If x was very large, e to the minus very large is what? It's 1 over e to the very large. E to the very large is incredibly large. So 1 over that is going to go to 0. 1 over 1 plus 0 is 1. So if x is large, it goes down to 0. And if x is very small, what do we get? If x is minus infinity, minus very large, minus times minus is positive. E to the positive big number is a big number. 1 over a big number goes to 0. So the great thing about the logit function is it determines a probability. It's a probability that goes to 0 as you get far to the left of 0. It goes to 1 as you get far to the right of 1. Okay? And that, if you think about it, is kind of what you wanted over here. If that probability, if we had a logit function sitting on this example, what is that going to do? It's going to give us the probability of the thing being male. Okay? If male was to the right, okay, over here Superman would have a probability of near 1 of being classified as male. This guy would be, classified as male greater than 50%, because a guy at 0 would have a 50% probability. Maybe this is 80%, maybe it's 90, who knows what it actually is. But it's clear that if we had a logit function here, if our data was well behaved so that we were making a decision based on a decision variable, where the more positive it was, the more positive the decision variable was, the more positive confident we were that it was a positive example. And the more negative the decision variable, the more confident we were a negative thing. The logit function gives us a ground to reason about this. Okay? Any questions? Now, one thing about the logit function here I define it as with a constant c over in the exponent. That doesn't always appear when you look at your book. What is the effect of c here? Okay? What happens if I make c really big? What is the logit function going to look like? Okay? What? It will flatten out? Okay, suppose, let's do this so I don't get confused, because it's easy for me to get confused on this. 1 over 1 plus e to the minus, let's say, 1,000,000 times x. I guess with the graph I should be drawing is 1, where that's 0, and this is x, right? What is going to happen as, this means that if I compare this with when e was 1, when c was 1, I got a nice smooth thing. What's it going to look like when when I have a large constant here? Okay, it's going to react much more quickly. Does everybody agree? What does more quickly mean? It's going to get really squared off. Okay? That being slightly greater than 0 is going to have a big effect. Does everybody see that? So a big constant turns it almost into a square wave. Okay? Whereas a small value, 0.0001, is going to make for a very, very gentle transition. Okay? So by picking what our decision variable is, and we can view that not just the decision variable, but c times x, this is a function of the decision variable. Okay? What we're going to try to learn is what is the best function of the decision variable to do the classification. Okay? Any questions? So what are we going to do? We are going to say that if we have m variables, okay, we are going to be trying to learn in some sense, steepness parameters, okay, how it's going to react to the input. By trying to learn a score, okay, a function, namely the weights, w times the variables, where we're going to come up with a linear function of the input variables. This is what we want to learn, okay? And the classifier that we're going to want to build is going to be, given our input record, x, okay, we're going to compute our hypothesis on that input record and use that as the exponent for our logit function, okay? And so the goal is really going to be learn the weights of this linear function so that the logit function, which returns probabilities, the classification probability for each element, is optimal, okay? So we need to have a loss function to decide what is the best, what are the best weights for this linear function in order for it to behave well as a classifier. Any questions about that? Okay. Now, what is the right loss function for a regression thing? We're going to have n training examples. Each of our training examples are going to be in either class 1 or class 2, because a binary classifier. What we seek to do is to find the coefficients that will give a high probability on positive items, okay, and a low probability on negative items, because we're trying to figure out the probability of this example being positive, okay? And so our loss function is going to be something that makes a judgment on the probability that we give for an item being positive, okay? Any questions? What is the shape of the error that we would like to have? Okay? I claim that we want a shape that is something like this. Okay? Suppose we have a positive example. Okay? And we want, okay, let's just think about what this thing is doing. If we have a positive example, we want the probability of it being positive to be 1. Does everybody agree? If we have a negative example, we want the probability of it being positive to be 0. Okay? So the x-axis is going to be the probability of it being positive. Okay? These lines are going to denote what our cost function is, the desired loss function. And the loss should be as follows. If the item is a positive example, and we say that we're 100% sure it's a positive example, we shouldn't lose any points. We get full credit. If we say we are 80% sure that the item is positive and it's positive, we should lose a little credit. The lower our positive probability, okay, the more points we should lose. But eventually, if we say that we are 100% positive it's negative and it's positive, and the example really is positive, we should take a very big hit here, an infinite hit. So the claim is the shape of a function that does this, okay, is kind of what we want for our error function. And it turns out that the logarithm is a function that has this shape, okay? So what is the logarithm of 0? What is the logarithm of 1? What do we have to raise something to make it 1? It's 0. And what is the logarithm of 0? Infinite, okay? So the logarithm certainly has the property that at both poles it looks like that. And, you know, it's kind of a slow transitioning thing. That's what logs do, okay? So the log is kind of has the kind of shape that we want. What is the difference between the red and the blue line? Okay? It's clear that for a positive example, you want it to lose no points for it being equal to 0, for saying it's 100% positive, and you want it to lose infinite points for saying it's 0 point probability of being positive. Okay? For negative examples, it's kind of the opposite around. You want to say if the thing is negative, the probability of being positive should be 0. And you should get punished, and if it's negative and you say the probability of it positive being high. These two cases are clearly symmetric, okay? And what is the difference between the two of them? The claim here is that basically if you instead of having, for a positive example, the error is that loss function that you want to pay is minus the log of the probability of it being positive. Okay? Why is it a minus log? Okay? Well, we're dealing with probabilities, right? So all of these things are going to be, when you have a value less than 1, okay, the log is going to be negative, right? So the minus is in order to make these things positive, okay? And the difference here is that we want one to be a reflection of the other, and if you work it out a little bit, if you take 1 minus the hypothesis, that's what flipping this thing is at, that's what flipping the cost of these things are, okay? These things should be equal at 1/2. 1/2 and 1 minus 1/2 are equal to each other. This is how you flip it. Any questions about where these loss functions come from? Okay? And this is basically what I'm telling you here. Okay? That we want the cost of a positive example to be minus the log of the prediction of its positiveness, and for negative examples we want it to be the log minus the log of 1 minus the prediction of its positiveness. Basically, 1 minus the positiveness is the negativeness, okay? And that's kind of what we want to have here. Any questions? Okay. So what is the loss function, okay, of the logistic regression? It's basically going to be the sum of the costs for every example in our training set. Okay? Now, what is the cost of an example? It depends upon whether or not that example is positive or negative. So for each one of these n terms, we either want to pay a cost for it being a positive example or a negative example. Okay? There is a cute formulation here where we can write it as the indicator variable. Remember, the class variable indicating it's a positive class was 0 and a negative class was 1. Okay, or maybe it was vice versa, but there's 0, 1 are the indicators of the class. If we multiply it by, if we weight the positive value times the label, the indicator variable, if the positive example, if it was a positive example, the indicator variable was 1. If it was a negative variable in value, it was 0. This made only one of these, this meant that this was either going to be turned into a 0 or it was going to be added. 1 minus an indicator variable is also either 0 or 1. And this is going to be 1 when this is going to be 0. Okay? We can use these coefficients to basically select which one of these two error terms to use. That's what's kind of cute about the formulation. Okay? So we're going to sum up n terms. Each of these n terms has 2 clauses in it. Only one of these clauses will apply, depending upon whether it's a positive or negative one, and we will pay the appropriate loss function for it. Okay? Any questions about that? So what's good about it? It turns out that this loss function is convex. Yeah, question.
I had a question on the. So it's written in the end that this works if both the variables are 0 and 1, right?
Yeah.
So in a case that we assume the class variables not to be 0 and 1, and let's say 1 and minus 1, do we have to change the cost function accordingly?
Well, okay, so you're saying if instead I use the class variables I say are 1 and 2, okay, will this work? The answer is no, but you'd be dumb to make them 1 and 2. These are just names, right? So it says you got to use the right names for the classes. If you said, God damn it, I demand that my class variables are be labeled 1 and 2, would that suddenly break this, or is there a way to fix this formulation? You just have to change this thing. Instead of this, if it was 1 and 2 instead of 0 and 1, what if I made it, replace this yi by yi minus 1, and this 1 minus yi minus 1, then it would work, right? So, you know, so there's no conceptual difference here. But yes, this is assuming this formulation here works because we are saying that the two classes are classes 0 and 1. Okay? Any questions? Okay, good. And if we believe this, if the loss function is convex, well, then by using our gradient descent stuff that we talked about last time, we can fit it, and therefore we can find the best possible linear separator between two classes. And again, this is linear in possibly nonlinear features, so you can do interesting things with it. Okay? Any questions? So when I use my ongoing example where we have men and women in height-weight space, the red points were the women, the blue points were the men. When we did logistic regression, this was kind of the separating line that we got, and it did a reasonably good job. In general, it looks like for both the men and the women, it looks like about 3/4 of the points were classified properly. Okay? Any questions? But where were we making our mistakes? Does anybody see where the mistakes were made? What are the mistakes? The mistakes were the red points in the blue region and the blue points in the red region. Where are the mistakes in general when you look at this thing? Okay? Generally, I think the mistakes, again, you have some weird outliers there, but most of the mistakes are what? They're relatively close to the decision boundary, right? What is it that logistic regression is going to do? It's going to get a probability of maleness for every one of these points. And undoubtedly, in the regions where, right near the decision boundary, the probability of maleness was probably not much, was over 50%, but not wildly over. So one of the good things about logistic regression is not only does it give you a, a classification, but it gives you a confidence level. Okay? Any questions about that? Okay, good. Now, there are a bunch of different issues that arise in classification, and that when you're trying to do classification in real data sets, there are some other issues that you have to worry about. One thing we'll have to talk about is what happens when you have more than two classes. This is interesting. There's questions about how do you how balanced are your training sets? And there's questions of what happens when you have really large numbers of classes. And there's different kind of techniques that you're going to want to use to deal with that. So let's talk about some of the other issues in classification. Now, suppose, we have a training set that is very unbalanced. And this happens quite often. Let's say you work for the airport security people. You'd like to try to identify a terrorist from a non-terrorist. They have many examples of non-terrorists, okay? They have one example of a terrorist. How would you build a classifier that did that, okay? Well, hopefully, first of all, if you've only got a small number of positive examples, if you really want to focus on, you don't know too much about the variation in terrorists. That's one problem that's clearly here. But there's a more profound kind of problem. Suppose you built a hypothesis where here is 0. Here is your, well, let's forget what the numbers are. But let's say that we have computed a terrorist score, okay? And our one known terrorist was over here. And all the other people in the world, okay, look like this, have a terroristness score distributed like this. What is the case? Okay, we expect that most people in the world, almost everyone in our data set is not a terrorist. Whatever score we have is going to have some fluctuation. Different people will look more or less like terrorists, depending upon who you're talking to, right? Where would you make this, where should the separator between terrorist and non-terrorist be? Okay? If you guys wanted to build a classifier like this, where would you want the decision boundary to be? Okay? Again, you can set it wherever you want. Different people can have different opinions. Where would you want the terrorist detector to be in this case? Okay, so he would like the terrorist detector to be here. Okay? Is that what logistic regression is going to want to do? Where is logistic regression going to want to put that terrorist detector? Okay? It's getting points for how accurately it's getting punished for the probability outside of 0 or 1 that it, in this case, it's going to confidently label every terrorist correctly, but the confidence is not going to be 1, and it's going to label every non-terrorist correctly with probability of 1. Where will the logistic regression classifier want to put the boundary? Towards where? It's going to want to put it over here. Okay? Why? That's raising its confidence on all these millions of people. Actually, all these millions of people that they are, Actually, wait, is that where it would want to be? Actually, that's not where it would want to be, right? If we move the boundary over here, it's getting prouder that it's calling the terrorist a terrorist with probability 0.99999 instead of 0.99. But it's lowered the score of the non-terroristness people. Does everybody see that? So where is logistic regression going to want to put that line? I think it's going to want to put it someplace over here. Okay? So it does get credit for classifying this guy right, and it gets in super credit for getting it there. Okay? Now, where do you think we would want to put the classifier? Okay? Any questions about that? Do people see that logistic regression is going to be tempted to move the line very close to the the logistic regression is going to move it very close to the small class, right? You wanted it in the middle. Is there anybody else that has another idea where they want the terrorist, non-terrorist line to be? You have 1 million people you have seen whose terrorist scores are here. One known terrorist has a terrorist score of here. Where would you want the decision boundary to be? Okay? I think this is a great place for it. Why is that? Because, well, all the non-terrorists are getting classified properly, because we've got millions of people here. It feels like we know a lot about what normal people look like, right? We don't know very much about what terrorists look like. So it might be that you want to put the classification here, okay? I don't know if you're convinced of that, okay? You don't have to be. It's an equal judgment. Different machine learning methods will put the boundary in different place. We agree that this was where logistic regression was. This method in the middle is by something would have been picked by something called a support vector machine, which is what we may talk about later. But what Skinner wants is something over here, okay? And we'll talk a little later about why we might want to convince the classifier to put it over there and how we can kind of do that. Any questions about that? Discussion, questions, anything like that? Okay, so this problem arises, okay, on the fact that when you have unbalanced training sets, okay, your classifier doesn't necessarily do what you want. It doesn't learn. It gets so much credit for getting the large class right. It tends to not get the small class right. And the small class is usually what people are caring about. If you're building a terrorist detector, it's not important to know who the most terrorist-like person in my class is. It's important to know the real bad guy from the rest of the population. Okay, so how do you how do you deal with an unbalanced class? Okay? The simplest thing to do is to make sure you get enough data on positive and negative, equal numbers of positive and negative examples. This is hard to do because often, in like the terrorist case, you can't make more real terrorists. Okay? There's a smaller number of them. So what can you do to balance the class sizes? Okay? One possibility is to work harder to find more members of the small class. This might be you look at all the terrorists through history, okay, and you try to build them, okay? One other way to make the classes more balanced is to throw out some of the elements of the big class, okay? Now, ideally, we'd like our classifier to be 50-50. How many elements in the terrorist, non-terrorist case would we have to throw out to make it balanced? Okay, all but one. Okay, now that seems pretty extreme. Okay, but again, it's not an unreasonable thing when you have a wildly unbalanced class thing to throw out some of the elements of the bigger class. Another idea is to weigh the minority class elements more heavily. One way I could get a class size, two equal class sizes, is making 1,000,000 copies of the point of the one terrace that I have, right? And then my distributions would look something like this. And then the logical thing would be to put presumably the splits, the decision threat boundary somewhere between them. The good thing about weighing the minority class elements more heavily is it does make it more balanced. The bad thing about it is that it creates a big danger of overfitting. Okay, if you have 1,000,000 copies of one terrorist, you're going to think all terrorists look just like that guy. Okay? So, a useful idea is to create synthetic members of the smaller class, okay, by replicating them with some kind of a random perturbation. You might imagine you take this one terrorist and you know their height and their weight and stuff like that. Maybe you add some random noise to this kind of thing and you create a bunch of synthetic terrorists that look like that. Okay? Any questions about this? Now, the question really is, if you're going to add random noise to the terrorist, how much random noise would you want to add? Okay? You kind of get the idea of what I mean by creating random people. Okay? You add something to their height, you add something to their weight, you add something to their age. Okay? When would you think that I've added too much stuff? How would you tell if I add too much random noise versus a little, too little random noise? Would there be any criteria here that you would distinguish it? What would this picture look like if I added too little random noise around the positive example? Yeah? It would be something like that. When would I have added too much random noise? Okay. When it's too wide, what would too wide be? Well, one thing that would be bad is if it started to encroach on the examples of the negative one, the negative ones, right? So how could you figure out how much random noise to add? Maybe it's a parameter. You try it, you train your classifier, you evaluate it on your holdout set, you try it with different amounts of noise, and you see where it does best. That would seem like one way to do this. Any questions about that? Now, there's another way of creating random people or random data values that's almost as simple, but does a better job of solving a lot of these problems. Okay? Suppose we have a class, a world like this where we have a lot of positive examples and a small number of negative examples. Okay? I want to create enough synthetic values so that my positive and negative values are there. But I also want to create my synthetic values so they are in the right place. Where is the right place? The right place is kind of in the empty space between the positive examples and the negative examples. So there is this technique called SMOTE that works in the following way. Suppose, let's say I have a positive example P, okay? I will find what are the nearest neighbors of my positive example, okay? For this one, maybe this and this and this are my nearest neighbors, okay? For this point, it's all going to be the other, the negative examples are going to be my nearest neighbors. What am I going to do? I am going to pick one of my near neighbors and then a random number between 0 and 1 and produce as my synthetic example my real value plus the vector difference between me and my nearest neighbor. Okay? Again, every one of these points is in feature space. It has a height, it has a weight, it has an IQ, it has an age. Okay? What am I going to do? I am going to let, if P is my positive example and N is my near neighbor, N minus P is going to be the vector of feature differences between me and that point. If it's a near neighbor, these vector differences should be fairly small. But if I now multiply it by some constant between 0 and 1, I'm going to have the property that I'm going to be adding a point on a straight line between me and my near neighbor, somewhere on that line, uniformly on that line between me and my near neighbor. So what's kind of cool about this? If I do this a bunch of times, I am going to populate the empty space rather with my new examples, rather than crowd into the space of the negative examples. Any questions about that? Okay, so this is a good way of randomly constructing training examples, synthetic examples that are in the right place. Any questions about that? Okay, and this, any questions? Okay, so this I like. Okay, so we agree that we can, we can now create balanced training sets or relatively balanced training sets if we want. What do we do when we've got a classification example that is a task that isn't binary? Okay? Again, on your news task, there were 4 classes, as I remember. On your image processing task, there were 10 classes. Okay? So, what could we do? Okay, again, I think of this as now that you've got points in feature space with k different kinds of labels, and your goal is to, in some sense, try to build separators that lie between the classes. In this case, the right thing to do would be, we'd like a line here, goes up to there, goes down to there, okay? One thing to note is that when you have multiple classes, it's no longer the case that a line can necessarily cut off one of the, even if it is well-formed clusters, there isn't necessarily a line going through it that cuts through all of them, that cuts off one of these things. So how can we deal with multi-class classification? In the example I showed at the beginning of using linear regression, we had positive classes being labeled 0 and negative classes labeled 1. You could have generalized this by having classes, if you have k classes, have them be labeled from 0 to k minus 1. What's bad about that? What's bad about that? Well, what's good about that is if your classes naturally have an order to it, okay, this is a perfectly fine thing to do. So if you're trying to predict how good a movie is, okay, and movies are labeled as 3-star movies, 4-star movies, 2, 1, the classes then have an order to it. And trying to predict the number of the class kind of makes sense. If you have classes, though, that are not ordered, okay, trying to predict the class number as a regression problem is a bad idea, okay? We agree if, let's say, lightness of hair were to be, you know, blonde would be a 0, brown might be a 1, where would red be? Okay, there's not a linear order of the colors here. So trying to predict encode classes by linear things is bad unless there is a truly linear order of the classes. Okay, any questions? So generally, when people are trying to build multi-class classifiers, what do they end up doing? Okay, you end up building a sequence of one versus all classifiers. Okay, you turn the problem of trying to classify the item into one of k classes into building k different classifiers, each one of which is trying to separate the given class from everything else that's not in that class. Okay? So on this example, if we have these set of points, we're going to reduce our 3-class classification problem into 3 binary classification problems of green against all, squares against all, and reds versus all. Okay? And these we could each use logistic regression to try to build a good separator between them. Any questions? If we do that, the natural tendency would be to say the identity of a point is going to be, for each, if we did logistic regression, the classification here is going to tell us what's the probability of it being green. The classifier here will say what's the probability of it being a square. And here we would have the probability of it being red. And then typically you would take the largest probability as being the indicator. The simplest thing to do is to use the largest class probability as being the label you get for it. Any questions about that? Okay. Now this idea of using separate classifiers for each class end up getting to be harder, ends up working less well as the number of classes increases. Okay? Sometimes you have a problem where there are a small number of classes. That's kind of what we saw here. Okay? In general, if you have k classes, the probability of guessing what class the item is only going to get right 1 out of k times. So classification becomes much harder if you have to choose between k classes. And there are different issues that arise when you've got lots of classes. One is certain kinds of mistakes are more acceptable than others. Okay, it's probably okay to declare a truck to be a car, but it's not acceptable to declare a truck to be a cat. Okay? The other thing is that when you have lots and lots of classes, okay, the more classes you have, the smaller the classes actually tend to get. Even if you have an equal amount of training data, it's still the case that it's rare that if you're doing a classification problem, if you have k classes, the probability of somebody being assigned to each class is certain classes are rare. If we think about our terrorist problem, we'd like it to be the case for fitting our classifier that we have an equal number of terrorists and non-terrorists. When we test our classifier in the world, we'd better have very few terrorists coming up, okay? Because there aren't really that many of them. And so this problem gets exacerbated as you have more and more classes, okay? So we have to deal with that. Any questions? So when you have a huge number of classes, okay, one of the best techniques, okay, to deal with it is to build some kind of a hierarchy on your classes so that, similar classes are grouped together, okay? If you want to classify what a food is, there's thousands of different kinds of foods. But, okay, if you have a hierarchy where the top level says a food is either a meat or a vegetable or a grain, now you've got a three-class classifying problem, okay? And a natural way to try to do multi-class classification is if you can take your classes, group them into a hierarchy. This is basically clustering. If you could cluster classes by similarity, then what you would like to do? You would like to build a hierarchical classifier where at each node in this tree, you're going to choose between the siblings and then move down the tree, okay, until you get a leaf node. If we think about ImageNet, ImageNet was this famous data set of many of images in a huge number of categories. When I was looking at it, there were 21,000 subcategories, but there was a higher order 27 categories, okay? And again, if you make a mistake within a category, it's a lot more forgivable than it is if you make a mistake across across categories, okay? And doing your classification with a hierarchy makes it relatively efficient to do it, okay? Any questions? Note that in such a tree, if the tree is built right, if you have, if we had a classifier for each individual category, if n was 21,000, we would have to compare our example against n different subcategories. If we have a hierarchy, we're comparing it against only basically log n subcategories, okay? And so it's both more efficient and also more robust because the mistakes you make are likely going to be categories relatively close to each other. Any questions? Another issue in classification is that if you know something about the prior probability that an item was in a particular class, okay, this can help make your classifier much more accurate. Again, we once had a project where we were trying to classify all the people in Wikipedia according to what their job description was, okay? And you had certain rare classes where, like a rock star, okay, where a lot of people fit the category. Rock stars were young, rock stars were male and maybe a little grungy looking. There were a lot of people who were male and grungy looking, but relatively few people who were really rock stars, okay? So if you have multi-class classification, it helps a lot if you know in the world whether or not the class that you have is a what you call it, a class that is, frequently, labels frequently go to it or rarely go to it, okay? And the tool for updating this is Bayes' theorem. If we know in advance what the probability is of somebody being a rock star without any data about it, we can update our probability of whether this guy is a rock star based on what evidence that they have that they are a rock star. Okay? Any questions? There is a related classification problem, which sounds a lot like multi-class classification, which is multi-label classification. Often you have in a world where items can have more than one label associated with it. Okay? So if we think about it, in image classification, here was one where is this a dog or not? Well, this is a dog and a cat. So in images, you often have the case that images contain more than one thing, meaning that an image might really belong in more than one category. Okay? Your text articles, okay? If you want to classify is something a sports article or a business article? What is an article about a team getting sold? It could be a sports article, it could be a business article. It really kind of belongs in both categories. So how can you do what makes multi-label classification? The fact that there can be multiple different interpretations from it, different than multi-class classification, where there are a lot of possible labels, but we actually are going to stick it in one of the groups. Okay? Can anyone propose a way of doing using, let's say, the one versus all classifiers? How would we turn something like that into multi-label classification? Okay? Again, we've got a bunch of classes. We have, for each class, a classifier that says, are you a member of this class or not? To do multi-class classification, typically what we did was we took the probability with the highest value, okay, and said that you were if the probability of this image being a dog was higher than being a cat, we declared this thing to be a dog. Okay? How would you use that technology, extend it to multi-labeled classification? Okay? Where you're allowed to give it more than one label. Yeah? Okay, so the simplest idea is that you have a threshold, and any classifier that lights up above a certain threshold, you say that that's actually what it is. That seems like the natural way to do it. Now, one thing that makes it different is that there are, you might have some conditional dependence on whether or not the two classes are kind of seen together. Okay? So one thing that's probably true are, how do you tell the case of a dog? Dogs and cats are probably mistaken for each other reasonably often. Okay? In a multi-labeled classifier, if you just have the threshold of above a threshold, you're liable to say that any ugly-looking dog is both a dog and a cat. Okay? The techniques that are involved in distinguishing between multi-label classification and multi-class classification, if you know something about the distribution of classes in the images, you can now adjust those thresholds appropriately. So if the probability of something being classified as both a dog and a cat, if the dogness and catness scores are highly correlated, that might be an argument that you don't want to call everything a dog and a cat. You might want to make an or. Or if you say that there's certain things that are with dogs, so you know from examples that dogs are often posed next to dishes and they're posed on grass and there are things like that. If you can add extra data about which classes are kind of associated, what is the typical association between classes, this gives priors that can help label that better. Any questions about that? So multi-class classification is a related problem here. Any questions? The final thing that I'd like to talk about today is how do you normalize these independent binary classifiers to come up with a probability for each class. Suppose we have a 3-class classification. We can classify every person in here. We'll look at you. What's the probability you're a dog? What's the probability you're a cat? What is the probability you're a person? If you build 3 independent classifiers, okay, and let's say you're using logistic regression to train a one versus all classifier for each of these 3 classes, you're going to get a number between 0 and 1 that will say what's the probability you're a cat, what's the probability you're a dog, what's the probability of a, a person. There is no reason why these 3 probabilities have to sum to 1. They are independently trained, okay? Now, if you really want to think of them as probabilities, if your space of labels is, completely described here, you would want those probabilities to sum to 1. How do we make them sum to 1? Well, you've got to kind of normalize the probabilities, okay? So that given, you've got somehow a likelihood of being a member of each of the 3 classes, you want to kind of scale it so the likelihood sum to 1, okay? How can you do this normalization? The easiest way is to sum up the likelihoods of each of the classes to get t and normalize each value by that total. This is a linear scaling where you scale each weight to make it, and after this you're guaranteed that it sums to 1. In neural networks, they use a different kind of scaling mechanism for it that you've probably heard of called softmax. What is softmax? Softmax uses exponentials. It takes, in some sense, the output from your classifier, the ZI, and instead of normalizing it by the sum of the weights, it normalizes it by the sum of the exponential values of the weights. Okay? And this is what softmax does. And when you do this, again, because at the end, ultimately, you're dividing the total sum here into each of its individual components, the sum over all the classes is going to add up to 1. Okay? What is the difference between the linear scaling and the softmax? Okay? Is there any practical difference here? Okay? Now, the neural network stuff typically the outputs in neural networks are not fixed to be between 0 and 1. They can be, real values. Typically they're kept fairly small, but they're real values. Okay? So it's not a question of converting numbers from 0 to 1 into probabilities that sum to 1. But it's talking about converting a bunch of weights to something. The difference between softmax and standard normalization is that it's kind of the standard normalization is linear, whereas the softmax is linear in the values, where the softmax isn't. If I had was doing the normal linear weighting, if I had two quote unquote probabilities and one was 1 and one was 2, this would be 1 over the sum or a third, 2 over the sum it'd be 2/3. If I had 10 and 20, if I took the normalization here, it would still be 1/3, 2/3. The difference with softmax is that if the values are absolutely larger, the softmax probabilities get more dramatically skewed because there's an exponential function on this thing. So if you view these numbers not as being probabilities but as confidence levels, which I guess is kind of what the probability thing that you want to have, having a larger confidence, okay, even relative to the other value, you want to have has a nonlinear effect. So for 1 and 2, the probability of it being class 2 by softmax was 0.73. When the numbers got 10 times bigger, the probability skewed much more dramatically. So depending upon what your goals are, okay, how you got these numbers, maybe you want linear interpolation, maybe you want softmax. Any questions about that? Any questions about multi-class classification? Okay. If not, finish up your project proposals. I look forward to spending the weekend with them. And if you have questions about your projects, follow me back to my office and I'll be happy to talk with you guys. Okay, thank you and good luck.